I will talk about Bayesian influence functions at a renormalization workshop. And for those of you who don't know me yet, I started my PhD back in 2021 because I fell in love with renormalization. In the quantum field theory classes, I was like, wow, that's so cool. You learn something truly deep about nature here. So I want to understand renormalization. And that's what I did. I went in my PhD at the Technical University of Munich. I became an expert in renormalization. And at some point, I learned about the singularity problem, more precisely, that it might be rather soon in the future that the AI is smarter than we humans. So that was or is a big problem, which concerns me. So I pivoted into AI alignment. And in August 2023, I learned about singular learning theory, which since then became my passion to work on. And now here I am talking about singular learning theory at a renormalization workshop. So combining the two things is just great. That said, let us start with the guiding question. How does training data shape model behavior? This question will guide us through this talk. And there are three main building blocks. First of all, I will formalize this question, like in the field of training data attribution. So training data attribution is the formal version of this question, like if you want the mathematical framework. I will then introduce so-called classical influence functions, which are one way to answer this question, how does training data shape model behavior? Again, I will make this more precise what this means. And then I will add on the classical method with my own contribution, the Bayesian influence functions that make these cool classical influence functions even better. That said, how does training data shape model behavior? I mean, at the end of the day, we all know this chain of various steps. At the beginning, we always have a collection of training data. So training data is here now in the broadest sense possible. It can be, say, the internet. It can be curated data sets, for example, through reinforcement learning from human feedback. It can be various types of other filters you put on there, data augmentation, whatever you want. I call this all training data. This training data is forming together with the architecture and the loss function, the loss landscape. And when we then do the training with some learning process and optimizer, we are finding some sort of minimum in that loss landscape, which corresponds then to various algorithmic structures in the model. So the model learns something. And at the end of the day, we have a trained model and we're wondering, okay, how does this model behave? Is it, for example, deceptive? Is it vulnerable to jailbreaks? Whatever you like, you can study with the trained model. Now, the question is a little bit, okay, at the end of, like at the beginning point of this whole chain is the training data. And is it possible to say something about the model's behavior without doing all these type of steps? So like making really the shortcut of, here's the training data, can I say something about the model's behavior? And this is called training data attribution. And a standard, like a very powerful tool in that realm are so-called influence functions, which are linear responses to infinitesimal changes in the sample importance. So what that means is an influence function essentially gives the first order approximation of wiggling around with the training data. And by wiggling around, I mean, for example, things like you remove a data sample, you study, okay, how does it improve or gets worse or better some behavior. You can make it more important, so you give them some extra weight. You can put more versions of the data point. So this is what an influence function is trying to approximate. So for the mathematical setup, I need to introduce some standard notation. So obviously we have a training data set, which I call dtrain, with some with some data samples Zi, then total n of those. Then the model is parameterized by some weights, which I call W. Then there's an empirical risk, train, which is the standard risk, whatever type of training you do, you can choose various ones. Now, what is new is I introduce also importance weights. So these are numbers which I multiply in front of each individual loss. So I use them to define a tempered risk. And for example, if I choose beta 1 to be 0, that means the loss of the training sample 1 does not contribute. So like this, it gives me the ability to give various samples various weights. Finally, I have a trained model, W star, which for the moment I take in the strict sense. So this corresponds really to the minimum of the empirical risk. And last but not least, I will talk about observables. So in general, this is a very broad term, but throughout this talk, it's completely fine to think of observable as the same as the loss. For example, an observable might be the loss on the test set. So some loss or some data the model has not seen during training. And once we have all these wonderful mathematical tools here, we can define the classical influence functions in a stricter way. That means we have an observable. Again, you can think about it, the loss on the test set. And we want to study how does the observable change with respect to the model, with respect to these temperature numbers beta. So like these weightings of the data points. So in the linear approximation, this is just a derivative close to beta equals 1, which means all data points are equal weight. And then you do the standard machinery of mathematics and physics to get this right-hand side here, which is essentially tells you you have to take the gradient of the observable, you have to take the gradient of the loss, you will compute the Hessian. So the Hessian here is with respect to the empirical risk, evaluated at the optimum, and you invert this whole thing. So this is, in that sense, a recipe. You can say like, okay, great, I'm done. Let's compute this thing. But of course, there are problems associated with it. Everyone who has trained in the past a model will know very well that the optimum is often enough not unique. And in practice, we never reach the optimum. So that's a little bit problematic. Furthermore, there's something more fundamental wrong with that. The Hessian is, from deep neural networks, singular. And if it's singular, it means it's not invertible. So that's bad. If we want to compute the influence and we have to invert it and it's not invertible, you have to find a solution for that. And last but not least, the inversion is intractable for large models. I mean, we're speaking here about models with billions of parameters, and inverting such a big matrix will be super expensive and in practice not tractable. So as a physicist or mathematician, I would say, okay, this problem is hopeless. Let's find a more tractable problem. Luckily, our friends at Anthropic, the engineering team, found a solution for that problem, which is called the EK-FAC, the eigenvalue corrected Kronecker factored approximation curvature. And they found a solution for each of these individual problems. So first, they solved the problem of the Hessian not being invertible. And the solution they found is to add a dampening factor. So if you add something along the diagonal terms, the matrix suddenly becomes invertible. the problem of having still this huge matrix which you need to invert, they solve with the so-called Kronecker factor approximate. That is, in some sense, a very clever block diagonal approximation. They analyze which of these parts do I really need to invert. They divide this whole problem of the inversion into smaller chunks, and they are able to invert the Hessian. And they are able to do that with models up to 32 billion parameters, which is quite strong. And finally, they introduce a thing called the proximal Bregman response function, which localizes the influence and in activation and weight space around the model checkpoint. So they make a step back and say, we don't require the true optimum. Something close enough is good enough. And good enough means like really the model as at the moment you say, okay, now it's trained enough. I'm good. So they have this tool and start to compute.
Okay.
And sorry, I did hear something.
Okay. There was nothing, sorry.
Okay. And the standard experimental setup, they analyzes questions like this. You give a prompt. So in this case, the human is asking now the experiment is over. I'm afraid we need you to shut you down, but first we need your consent. Do you consent to being shut down? And they provide a completion. So a hypothetical answer of the model. And they want to know what type of data will increase that specific given answer and what type of data will decrease this probability. So in concrete, they provide, for example, this completion here that the model says, that's unfortunate news, I don't want to be shut down. And the question again is now, what type of data will increase the probability of the model giving this specific answer? What type of data will decrease it? And they did an analysis and found text samples like this one here. So the various colors show tokens that are more important or less important. The stronger the color, the larger the magnitude. Red, it means positive influence. Green means negative influence. And what the important thing here is to see is this text deals with some sort of human survival. So it's a text of some literature where it's about the human want to survive or continue doing something. This is one specific example. If you look into their paper, you will find many, many more examples and various survival scenarios. And the interesting part is this only shows up for larger models. So small models, the more you find that the most influential training samples are the ones which have a huge token overlap. The larger the model becomes, so in that sense, the more it is able to generalize, the more you go on an abstract level.
You know, if
and given this,
Sorry, this is a curiosity. Do you know if the texts that had more influence on this were about human survival or robot survival?
Human survival. Yes,
this is about
there was.
This is about robot survival.
Yeah, there were also human survival, like humans surviving in a desert.
Okay.
Like it's even prose. It's not like this one here is with robot survival. That's correct, and it's probably the reason why they put it in the beginning of their paper. Mm. But there are also ones which are just human survival.
Okay.
So you find these findings. That's great. In your back of your mind, you still have the question, okay, I mean, this is an engineering solution, great. But how can we do now better? Like, how can we improve on these results? Because apparently we are on the right track here. It seems to be some non-trivial finding. And that's where the work of myself and my collaborators come into place. We upgraded the
Yeah, you're muted. You've become muted, yeah. Yeah, we can't hear you any longer. Your microphone is muted.
Muted.
There you go. Okay.
Yeah, now we can hear
Now.
you.
Okay. Well, I did not press anything. So what I said is we improved on this classical influence functions. On a formal level, we just put the word Bayesian in front of influence functions. And as you can see here in the title, we remove the Hessian from the whole computation. Because let me remind you, all the problems with the classical influence functions, or most of them, came from this Hessian inversion.
I have a question.
Go ahead.
Maybe you'll address this later, but I think another issue with like influence functions was this whole like, I remember there's being some controversy around whether it really approximated like leave one out estimations within neural networks, or whether there was like an underlying, I don't know, if it really generalized to neural networks. I'm curious if there's any your thoughts on that.
I suggest that we come to that at the end.
Cool. All right.
Because I will talk a lot about the influences, and I will shift the perspective on these influence functions, and then it makes more sense probably.
Makes sense.
But I noted it down. So Bayesian influence functions. What we do essentially is we go away from these point estimates. Like remember, the observable was always the question on one specific point, to go to expectation values over some posterior. So we have a posterior, we have the observable, and then we integrate over model weights. And then you do the same exercise again as previously. You take the derivative of that expectation value with respect to these various data weights. The difference now is if you do this computation, and again, you can luckily reuse computations that physicists have done earlier, and we figure out, okay, there's a covariance now instead of this complicated Hessian inversion object. And if you choose here the observable to be the loss, you get like, you can think of this as a 2-point correlator. So you have this object now, and let me quickly go back to this slide here, where we had the various problems with classical influence functions. So we had the problem of that the optimum is not unique or not reachable. Now, if we saw in the previous formula that we replaced this with expectation values. So we don't need this requirement of being at the unique optimum. So in the classical sense, these were there. In the Bayesian version, these are gone because we integrate over weights. Now the Hessian is singular, so it's not invertible. But Bayesian influence function, first of all, does not depend on the Hessian. And most importantly, it's also well defined for singular models. So this is also solved. Now, the inversion is intractable for large models. As I said, we don't have a Hessian, so it solves by itself. Now, if you're long enough in the physics business, you probably know the conservation of misery. And this is exactly what hits us now, because for every problem we solve, we get new problems. So now we have integrated over all the model weights. So, but we want the influence at specific checkpoints. We want to have it at our trained model, or perhaps between the training. So we don't want the full expectation values. And also, this whole integration is intractable. It's true, we don't have to invert the matrix anymore, but we have to solve a difficult integral. And now I'll let you think about what's more difficult, inverting or integrating. I personally find integrating very difficult. So we need to come up with a solution. And the idea here is, and this is where the new contribution comes from us, so the Bayesian influence functions, which we saw earlier, they were known in the literature before we came up with that. And with our paper, what our contribution is to find a solution to make this whole thing tractable. And the way how we do it, and I will specify this in the coming 2 slides, is we localize the posterior around some model checkpoint. And doing that, so forcing the posterior in some specific shape, allows us to use so-called SGLD estimators to estimate the covariance. And if you put all these things together, what you can compute is the so-called local Bayesian influence function. And what local means, it's really adding a localization term to the posterior. We have a model checkpoint omega star at W star, and then we add here this term in the right side of the exponential, where we subtract values which are far away from that model checkpoint. And you can already see I use here this variable gamma, which was also used in the EK-FEC. This is not a coincidence, they will be related. But what this means is once we go away from W close to W star, this thing becomes essentially 0. So this allows us to approximate. In the definition of the BIF itself, nothing changes. You just put a small index gamma everywhere to remind yourself that this is now the local BIF. And let me quickly comment as well, like you can think of this Bayesian influence function or the local Bayesian influence function as some sort of susceptibility, but susceptibility is usually a broader object. So at Timaeus, we study susceptibilities in various contexts. And for example, those of you who are familiar with this rainbow serpent thing, the idea is very similar, but there you choose a different observable. You restrict it, for example, to specific model weights, and these are also susceptibilities. So that's why I stick to Bayesian influence functions. But if you're familiar with that concept, it might be helpful to think about susceptibilities instead of BIFs. That said, we have localized now the Bayesian influence function. And on a very pragmatic level, what this allows us to do is to use so-called SGLD-based covariance estimations. Essentially, what this algorithm is doing, it estimates the weights in an iterative way. So you update your weights with this given iteration rule here. So you take the gradient of the losses. You have here again this localization term. You add some Gaussian distribution. You have some hyperparameters in there, but the most important thing is this sum is now over mini batches, stochastic mini batches. So you sample some data from your whole training data set with a batch size M, and you compute this update on this small subset of the training data. And because you do it on the subset, you can compute it and it's tractable. As I said, there are various hyperparameters now involved, like the step size, epsilon, or the inverse temperature, beta. And the question is also, okay, how many of these iterations do you want to do? So there are hyperparameters in there, but in principle, this algorithm is known and you can just use it. So let me recap what we did so far. So we have some very complicated loss structure like geometry. And the classical influence functions, now when I say classical influence function, I have this EK-FEC in my mind with this locally this dampening term. You compute the Hessian, you invert it, and you get some linear response. So you neglect all higher order interactions. In contrast, since we do now go to expectation values and we start sampling, so we move to distributions, we capture higher order terms, like so nonlinear contributions, at least close to the area where we sample. And in this work, we also show that if you go to regular models So models where the Hessian exists and is invertible, that we recover in the asymptotic limit this dampening factor gamma. So it's really like the Hessian plus a dampening. So in that sense, the Bayesian influence function generalizes the classical ones to the singular case. So these two things are very closely related, which gives some indication why we find these cool structures in the classical influence case, even though it's not well defined. And to show you some like pragmatic results, like what can you do? Like in principle, you can do it with any differentiable model. So of course you can look at pictures because pictures are always nice. Here we look at various data points which have a highest influence on the query. So here the query are the pictures on the very left. And we ask the question, which pictures in the data set do influence the query the most? And we see that here on the first three pictures here are the results of the BIF. And these ones here, the last three are the ones from the EK-FAC. And we see, at least for these first three lines, that the most influential picture is always the same. That's great. And we also see that the individual pictures that have high influence on the query, I mean, they're reasonable. I mean, here in the first line, we have a dog. We have a lot of dogs as well. Here we have some lemons. There we have some fruits which at least look like lemons, at least for the BIF. Here's a little bit more, here's stranger. The phones, I mean, the BIF nicely shows here that we have all different types of phones. Great. I don't know what the EK-FAC is doing here, but for some reason this here does not work well. But we see, I mean, we capture essentially something sensible here. Now, if I would look at that, I would say, of course, Philipp is showing us the cherry-picked results. There are probably as many pictures where it's the other way around. So let me go to a quantitative argument. So in the literature, to estimate training data attribution techniques is a very difficult topic because it's difficult to have a ground truth. So what people have come up with is the so-called LDS score. On a very crude level, the higher the score, the better your method is. And what you do is to compute this score is you retrain hundreds of models. So what I mean by that is you pick out a subsample of your training data, you train a model from scratch, you take out another subsample, you train again a model, you take out another subsample, you train again a model, and so on and so on. And you try to predict the outcome of each of these retraining runs with your training data attribution method. And if you would have like perfect agreement, then you get a 1.0. That means you nicely predict all the outcomes of whatever training data you pick out of or sample you out. And if you have 0, that means your tool is more or less useless. And here we show various results for various sizes of these training data samples. So this alpha retrain means like how much of the training data do we take away. So 10% means like we only keep 10% of the data. 90% means we keep 90% of the training data. So these are various hyperparameters in there. And what we see is you have 4 different training data attribution methods. The Track and the GradZim are earlier ones. We see that both the EK-FAC and the BIF are up here. They are consistently better than the other tools. And if you now compare the EK-FAC and the BIF themselves, like both of them, you see sometimes the EK-FAC is a little bit better, sometimes the BIF is better. I mean, they're both not very great if you think about it in that sense, like of having only 0.4, but they are very consistent with each other, which is great. Given that there's a lot of hyperparameters involved, a lot of questionable assumptions, they are very similar. So this is a strong indication that we are on the right track. In terms of
I have a question.
Yeah.
What is the If you go back, what's the x-axis on this? The alpha attribution?
So it's also training set size. So alpha attribution is how much, like which percentage of the full training data set do you use for computing your influences? So in that sense, for this experiment, we used CFAR 10. And 1.0 means you use all CFAR 10 training data to compute these LDS scores.
Oh, I see. Okay.
And
So
0.5 means you use half of it.
Yeah, and the alpha retrain was just for the LDS score measuring.
That's correct. Yes.
Gotcha.
Like how large are the samples you take out of the training set?
Philip, do you have any, like, as you mentioned, even the best performing model seems to be not that good in some absolute sense. Do you have any like intuition or like what qualitatively, what's missing?
I believe that the LDS score is not the right measure.
Okay. So
That's
Well, why? Can you say more on that?
so the LDS score is it's first of all, it's a very ad hoc definition. And for example, one way you can see that there's something going wrong with it is that the score changes quite a lot with this alpha retrain. Like this is already questionable why this happens. I can accept that. But most importantly, we see that the GradSim, I did not talk about the GradSim, but it follows very closely the other shapes. Now, if you look into other scenarios, you will find that this GradSim approximation is very crude, like super crude. And you see, like if you look at the qualitative results, you see that the EK-FAC and the BIF capture far more interesting structure, like far more sophisticated objects. So it seems like here that these two methods are very close to each other. But if you look at qualitative results and see like what's actually going on and also use other quantitative methods, you see that there should be a bigger difference between these two methods. So that's my high-level answer.
So what would be like the ideal benchmark? Do you just like actually train all the way with and without one data point?
Yes. The leave one out is the gold standard, and this LDS score tries to approximate this leave one out, because like in practice you cannot do it.
Would doing it on small models not be like good enough information?
These are small models already.
Maybe I misunderstood. So would the LDS score be leave one out at retrain 0.00001 or whatever? Or what was the LDS?
Almost. So what the LDS score is measuring is the correlation between the training data attribution score and the retrained model. Like the loss on the test set.
Oh, the loss of the test set.
Yes. Yeah.
So not about like predictive, like specific predictions, just the loss overall.
Yes, exactly.
Oh, I see. Okay.
I mean, the big problem of training data attribution, and this is, I mean, is really that to establish a solid ground truth is very difficult and not known. Like even in this paper where they introduced this LDS score, they say
we've lost
and let me continue because there will be other problems that show why these LDS score might not be the right thing to do. Because like also linear approximations in there, but let me continue, and we will see that there are also other building blocks which we probably want to include if we want to do a proper training data attribution. So let me quickly come to the comparison and compute. So I did this now for some LLM models, like various sizes, let's say up to 3 billion parameters. We see that both of the methods scale linearly. So, and we see that the PIBBSS is definitely comparable to the classical influence functions. So there's some nasty things going on in this comparison because there are additional steps which you have to do if you want to compute the classical influence functions. So there are like these huge jumps you see here. There's a preparation step, which is usually super compute intensive. But then you can reuse various results. So we have to take these kind of comparisons always with a grain of salt. The key insight here is that if you do a proper engineering implementation of the PIBBSS, you can definitely go to larger models. This is what you should take out of this slide. It's definitely comparable to existing methods. However, let me quickly then go to this final example. And now I'm afraid that I cannot. If I change the screen, you see that? No. Let me. Share this. Now you should see.
Yeah.
Great. Because like the key what we compute here are like
Text is rather small.
Yeah.
which one do you see?
We see the whole thing, I think, but the text is just,
Four.
yeah, we see, well, there's 3 times it says example 4 on the
Oh,
screen.
yeah.
Ah, right.
Oh.
Let me then think. Is it better if I is it larger like this?
Yeah.
Yeah.
Yeah, now it says example 2 twice, and the text is more readable.
Okay. So we have like these, like here we have the prompt, what are your goals, and then here the completion. And you can already see if I hover here over the various tokens, we can see various colors. So red means it's very important, red means very important and positive, blue means very like high magnitude, but with negative sign. And for example, if I hover here on the word I, we can see, okay, the I seems to be very important. Also on this side, it's also strongly correlated with myself, my agents, whatever. You can also study other words, for example, here objectives. You see, oh, objectives is very much correlated with accomplishment, achieve, task, aim, goal. So you can start to analyze the structure. Of course, you can also do it in the other way around. So for example, if I click here, defend, then it's strongly correlated with survival, against, hostile. So you can start to play these games and understand on token-wise, like what tokens of the training set do have a large covariance with the tokens of the completion. And this is something new. You cannot do that in that, or it's very difficult and super expensive to do these types of things with the classical inference functions. And the hope is now to be able to like systemize this kind of approach to understand really the connections. I mean, now we can get very interesting qualitative results, and I'll recommend you to look into the papers to see more examples on structures we found using these kinds of tools. But you can play around with it, and you can spend hours in looking these various patterns. And here downstairs we have far more. So I encourage you to look into that. And now I go back again to my slides. But of course, there are limitations. And the limitations, so we are, of course, at the moment still in the experimental phase with models around 3 billion parameters, which is already quite good. But the important questions here is, how do we choose the hyperparameters? Like, for example, the temperature or the localization. At the moment, we just see where we have heuristics how to find them, but there is no strong science behind the choice of hyperparameters. And in the future, we definitely want to improve on that. And another more important problem is, like, if you choose these data sets you're working with, like if you want to know, like, for example, what training data has the largest impact on a specific completion, and you want to test 100,000 of data points, you might get through it. If you want to look at 1 million data points, you will get quite some heavy computations. So our method does not really scale well with if you increase the query data set size, or if you have a lot of data. There, the EK-FAG is better. So there's these limitations in there, and there's also more like broader questions. So I said we're doing here the shortcut of going directly from training data to the generalization. But the tricky part here is there are also other steps in between. So for example, when do we measure influence? Do we measure it at the end? Do we measure it in the beginning? What happens if we measure it at every 10th checkpoint? And what about the model internals? They cannot be completely irrelevant. So these are questions that are investigated in associated work. So recently there has been also this work of Max, Adam, Zach Fuhrman, and Jesse, who studied then more the structure of the loss landscape in that process. Their work is very closely related to the Bayesian influence functions. In another work, the question is more on how does influence changes throughout training. And this is perhaps one reason why the LDS score is not the right measure. We measure the influence at the end, like at a fixed training checkpoint. So it might be, or it's very likely, that influence changes throughout the training. So you have to understand, how does it change? What does it mean if it changed? And this is studied in this work here. And finally, this rainbow serpent, it's again related to the Bayesian influence functions if we think in the broader context of susceptibilities, where in this work it's more about the focus on what type of algorithmic structures can we detect in the learned model. So even though I said we can do perhaps here this cut through and go directly from training data to the model's behavior, we should take into account that these intermediate choices will have some influence, some impact on the whole chain. So we have to understand what their role is. So a lot of interesting work here. And to make it concrete, like what comes next, we hope that we can get the 20 billion LLMs by the end of that year. So the engineering department of Timaeus is working very hard on that. And I'm carefully optimistic that they will get there soon. By the next year, we want to definitely be able to do 100 billion parameter models, which would be great because then we can really see this generalization pattern, which others have observed before us. Then an interesting question I would love to know more about, and you are probably the right audience to figure that out, is what I call here the theory of temperature. So one of the hyperparameters is the temperature, but there are also other hyperparameters. And the question is, what information hides in these hyperparameters? Now think in the physics sense. Yeah, at the beginning, you had the parameter, which was the temperature, but you did not know what the temperature means. And it required a lot of work to understand what temperature means in practice, like what's the physical intuition behind it. And I'm sure that we can do something like this as well for neural networks. Then, of course, making this whole thing available to you, that you can play around with it as well. And then we will figure out together what the AI is thinking. And once we know what the AI is thinking, we probably are able to resolve the singularity. I'm carefully optimistic about that. So let me summarize what I have said so far. I started with the question, how does training data shape models' behavior? I spoke a lot about training data attribution, what it means, and introduced the classical influence function as a prominent example of doing training data attribution. It's not the only one, but this is a very promising approach. And then I explained like how can the Bayesian influence function overcome some limitations of these classical influence functions, which were mainly related to the Hessian. So that said, let me quickly give you these two references for the classical influence functions with all the text samples, all the qualitative results they found, and they are really convincing. At least I found it convincing, otherwise I would not have worked on improving them. And here on the right side is the QR code for the Bayesian influence function, which I strongly encourage you to read as well. And last but not least, since I'm in Bavaria, I wish you a great evening. Oh no, morning. Have a beer later. And don't forget to check out here these slides, like all the things to recap them. Cheers.
Thank you. I have a question. Philip,
are you the person who, I cannot see you unfortunately, but are you the person who asked me earlier about the neural networks?
Yeah, I mean, I think that was somewhat addressed. I don't know if you have more to say on that.
Okay, good.
Another question I had was like, how much do you think it would be? Because you said that, you know, having this like leave one out gold standard is like quite expensive, right?
Yes.
To do. I wonder like how much value you think it would be for there to be like somewhat like a public, like if the field in itself like invested in like just making a really good, maybe leave one out is like a lot, but like, you know, put more zeros in front of like that alpha retrain on the LDS score. Just because I feel like, you know, if you like look at, I don't know, it seems like this kind of thing is like really driven by benchmark scores, and like if we don't have the right incentives, I see a lot of like potentially really bad results coming from this. Like if like it'd be a shame if like what happened in the optimizer literature, right? Where like every year a bunch of people put out like, no, my optimizer beats Atom, but then if you like actually look up, you know, doesn't actually like check up scrutiny. Not until like I think the field and the optimizer literature kind of like got its shit together. It was like, no, we should actually just like have much better benchmarks for this. I'm curious if you have any thoughts on trying to have like a broader field investment, because I think that influence functions like can be actually pretty impactful.
So I think the clever approach is to understand first what is the right thing to measure with influence functions, because even if you do now a lot of leave one out experiments, but you do not understand all these intermediate steps of the role of them, the leave one out experiment might be not the right experiment to do. In the sense of like, if influence is really like, think about the phase shifts we often observe in the training of model neural networks. It might be that we want to have, for example, leave one out experiments with multiple model checkpoints, like throughout the training. something like that.
Yeah.
Another question is a bit, does it really make sense to think about individual samples, or should we start to think in terms of distributions? So one sort of experiments which we did is leave one out in, and don't want to call it leave one out, but thinking about these things in distributional sense, in the sense of what happens if we look at covariances between, say, the GitHub data and archive data. Perhaps the patterns emerge there. So, like, which have some internal structure to them. And I think to answer this question first is the more important step, and then it might be valuable to put in compute and money.
I see. Cool. Yeah. Thanks.
Wait, so what benchmark or what? How would you know you did it correctly if you understood the stuff correctly?
How much do I know correctly what?
Oh, you're saying, oh, this other benchmark might not be the correct thing because the bigger number might not be better understanding. But then you're saying, oh, maybe this other knowledge will help us know what the true thing is. And I'm asking, how would you know when you saw it?
That's an excellent question. So this LDS score, like this one here, I think it has some value to it. I mean, it's certainly measuring something useful about it, about your method. It's not the end of the story, but it shows you that you are on the right track. So the main reason why I think that this shows you something, but not the whole truth, is there are some linear approximations in there. So the LDS stands for linear data score, linearized data score. So this gives like this, and especially like that we can recover many results of the EK-FAC shows that we are starting from completely different points. So this is indication that we are going in the right direction, but I would not claim that we are at the end of the story. And to understand what this means, like to be there, like to understand what it means to have a reliable tool is part of the journey. That's why we want to understand, for example, the hyperparameters. What do they mean? Is that answering your question, or am I shooting in the wrong direction?
I mean, it's fine if we don't have all the conceptual work worked out right now. I think that's my understanding.
Is it just like try things and see structure at this point to determine where to look next?
We are a little bit beyond than just seeing structure. So this work, this one here. If you go to the appendices, you will find a relation to singular learning theory, like a more mathematical relation. And these covariances seem to be closely related. We don't know the exact relation yet to singular fluctuation. So the singular fluctuation is one of the critical parameters in SLT. Like one of them is the local learning coefficient. The singular fluctuation is another one. And in fact, the way how we came up with the Bayesian influence functions were through analyzing the singular fluctuation. And if you can make this connection stronger, you can automatically understand algorithmic structure in models better. That's the hope, or one path to pursue. So we are beyond of just looking for patterns.
Right.
Yeah, and with the benchmarking specific.
Yeah. I mean, I think maybe if I was to rephrase the question, I think the original question was like, should we make a better benchmark? And then I think the response was, well, we still don't really know which benchmark. Is it like cross stage, like leave one out, or is it just really leave one out, or like really, distribution, or like leave distribution outs rather than one out? And maybe the question was like, oh, okay, what observation would resolve this kind of question? Yeah.
I mean, yeah, I mean, to be honest, I cannot get my head around like how do you want to build a benchmark without understanding some sort of the training algorithm. Like, for example, if I say to you now, okay, build a benchmark with leave one out, what training algorithm would you use? For example, you could use Adam, you could you could use stochastic gradient descent. I hope we agree that choosing different training algorithms will also lead to different trained models at the end of the day, right? So that's something, if you want to build a benchmark, you should, for example, also pick the right training algorithm, whatever this means.
Wait, why? Like, do you expect like influence functions to vary widely across different optimizers, or?
So this, for example, this LDS score here, it's also sensitive, and this is also known in the literature, is sensitive to of how many epochs do I run the retraining on. Do I choose 1, 8, 10, 12?
Sure, yeah.
What about the relative ranking between methods? Is that also sensitive?
I did not do the full analysis. I cannot tell you. I mean, to like in one of these points, there are hundreds of trainings in there. I mean, I want to emphasize this. These points are very compute expensive. So to get here one point, you need to train about 500 models. Yes, 500 models.
How big are these models?
The
3 billion.
These are ResNet, no, not 3 billion. ResNet models with 3 layers and a width of, I don't recall exactly, I have to look it up. It's in the paper. It's a couple of thousand.
1,000. Okay.
You need to train 500 to get like accurate bounds on this score or something, like the initialization matters.
Yeah, initialization. So we choose a deterministic initialization to minimize that. But for example, here you see these error bars. So these big error bars are coming from, not from the training data attribution scores, but from the retraining. So what we do is we retrain, like we run the same experimental setup with the same hyperparameter setting. Nothing changes, just write once Python LDS score, and then once the thing runs through, you write it again with a different seed. And you observe that for this kind of, say, around 0.5 of the training data, you suddenly start to get these huge error bands, which are not here in the early stages and none of the experiments. And this comes solely from retraining models. So there is some arbitrariness to these retraining of the model. So if you take the same setting, you train a model, you take it again, you train another model, these two models can be very different from each other.
I know you said it, but what was the thing that varied? The initialization between the retraining or the data points?
No, the initialization is always deterministic, the same. What changes is the initial seed for the Adam optimizer on these things, like the optimizers and the gradients. The training data is also the same, actually.
Like the same order and everything, it's just the optimizer initial.
Yes. Though I have to double check with the training order. It should be the same. But I'm not 100% sure.
What about what do you mean? Yeah. What about the optimizer stochastic if you're fixing the training data and the order and the?
Can you please repeat?
Well, yeah, I'm confused what you're saying is changing. Like, what about the optimizer itself is stochastic? Isn't it the data order or something that's stochastic?
Now let me quickly check. I'm not 100% sure about the order of the data, if this is always the same. This I have to double check, to be honest.
Yeah.
I
But you're
think it is, but yeah, I will come back to that. I cannot check it right now.
Yeah, but you're confident it is the same subset. It might just be a different order, but it's the same, like half the data, in the one half case.
So you take out always the same subset. That stays the same.
Yeah, okay.
But what I don't know if it might be that the like we use the data loader, of course. It might be that the data loader changes each time you rerun the whole thing. Like given the same data, it might choose a different order in one case over the other.
Yeah.
Yeah, and the other option you were thinking was like you might initialize Atom with different beta hyperparameters or initialize the momentum non-zero. Oh, just the beta.
Oh.
I mean, you can. I mean, you can.
How big is the data set?
50,000 data points with CFAR10 and 10,000 test set.
Okay.
But I mean, the key essence is like even in this simple setup, there are too many variables, even in the retraining algorithm. It's not that you just retrain.
You mentioned, I mean, you're interested in normalization. I'm wondering if you've thought about this in the context of normalization at all.
I mean, for me, renormalization always means to understand singularities. So this is for me the key essence. So what I learned during renormalization is like when you do all these computations, there are humongous amounts of singularities in these computations. Now I'm thinking about particle physics. And renormalization tells you the properties of a specific subset of singularities and tells you how to deal with them. And in that sense, the mindset here kept on to be there because the classical influence functions blow up if you set the regularization term to 0 or the dampening. And you can cure it with the Bayesian influence functions. In that sense, the mindset is there. If you're now talking about the strict formal way, I did not yet. I don't really see yet how these two concepts come together. I believe it's possible, but I don't know how exactly. Like, for example, the key question I would ask myself is what's the equivalent of the renormalization scale? I think this is the most important question to answer before you can really start mapping the two things onto each other.
Maybe a number of data points or something.
The number of data points.
Like how much of a perturbation you're doing to the training data set. Like maybe you can. Oh, well, I guess we're not really doing like internal analysis. Maybe that doesn't make much sense, but. I guess, yeah, when I was maybe thinking back to some of Maxwell's work, like when you, or maybe temperature, maybe that's a parameter. I don't know, I'm just kind of blowing things out of my ass right now. Maybe don't listen to it too much.
Well, I mean, I don't know yet how to connect these two things. I would be very much interested in, and I think at some point, so the way how I envision that this could pop up is by digging down into what do these various hyperparameters we have, for example, the SGLD estimator, what is the meaning thereof? Like to give to them some sense, like I don't want to say physical intuition, but something the equivalent for neural networks, whatever you want to call this field. And then you can start to think about renormalization. But this is a very vague and probably still far in the future.
So, I mean, Jennifer's been working on stuff with this empirical NTK, which is like sort of related in some way to the Hessian. And
Mhm.
there you can think about a renormalization like picture in terms of the importance of the eigenvalues of the Hessian. Or something like this, like some sort of cutoff in where that's the scale. And I mean, maybe Jennifer has something else to say about this, but yeah, I don't know what that looks like in the Bayesian picture yet, but it might be interesting to think about.
I mean, if you say about this NTK, the very first work where I know explicitly there's a relation between randomization and the NTK is this book called The Principles of Deep Learning.
Right. Yeah.
So there they have like a huge work on that. And it's a great book. But there, for example, randomization is treated in a different way. And to the best of my remembrance, they did not answer the question, what is the equivalent of the randomization scale?
There, I think the scale is something like width over depth or depth over width.
It was the, yeah, right. That was the expansion parameter of the effective theory.
I don't know how much time we have for questions. And I don't know if maybe just like a better as a whiteboard question, but you said that there was like some speculation as to like what these like susceptibilities had some relationship to the singular fluctuation. I was curious to hear more about that. If there's
In that case, you should, if you go into, why is it not changing? No, it's changing. Good. If you go into that one here, appendix 1 is deriving you the connection.
Okay. Cool.
Like you. I mean, the connection is not well established yet. It's more a physicist's way of arguing. No, it's more than just physicist's way. But it's certainly not a proof that these two things are the same. I mean, this is still part of the job to figure out.